Okay, so the last video got abruptly ended because of some internet issues. But yeah, so what we were doing is we showed you how to solve this, particular linear equation at the end. So now what we would do is we will try and go on to differential operators. Okay, so let's call this differential operators. And let's draw a line. So just as functions can be thought as infinite dimensional vectors, what Sturm-Liouville figured out is that you can think of linear differential operators in terms of matrices. So you can look at you know a particular operator of a form, say APX, DP, DXP plus AP minus 1x, dp minus 1, dx p minus 1 plus dot 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 plus a1 x ddx. And since I'm running out of space, let me move things around. And at the end of the day, you have some a naught. Okay, so this is a linear differential operator of the order p. This is a map on linear map on the space of functions. Since you have two functions, so this is first, let's say this is a linear differential operator. Operator of order p, and it's a linear map on the space of functions, since so L of c1 y1 of x plus c2 y2 of x is given by c1 L of y1 of x plus c2 L of y2 of x. So this is linear map. Linear map in space of functions, in function space. Okay. So the analog of the matrix equation that we were trying to solve, so the matrix equation was what? M of u is equal to f, right? So the analog of this here now is L of y of x is equal to f of x. Okay. So now for this, what we have to know, so what we need to know are these AIs, and we also need f of x. So once this is done, so these are known, and we need to find y of x from there. Okay, so that's what the rephrase problem is. Now, what we will be mostly interested in from now on is linear second order differential operators. So my operator that we are going to be interested in is going to look like p of x d2 dx squared plus r of x into ddx plus q of x equal to, that is the operator that we'll be interested in. And let's call this equation 1. Okay. So for any such homogeneous equation, something like L of y of x is equal to 0, this has two non-trivial linearly independent solutions, which is essentially y is equal to y1, y2 of x, and the general solution is y is c1 y1 x plus c2 y2 x. This is something that you guys know very well. When we are dealing with the inhomogeneous equation of L of L y of x is equal to f of x, then we seek a single solution y of p, and the generalized solution is then given by y of x is equal to cp into ypx plus c1 y1x and plus c2 y2x, right? So that is what but what happens is, in many cases, finding this particular solution is extremely hard and requires a lot of luck or guesswork. What the Sturm-Liouville theory is going to do is it's going to provide a more systematic approach for this. Okay, so this is what we are going to be doing. And so, all right, for the moment, what we will do is we will look at the second order equations, second order operators. So let's look at this second order equation L of y, and we define this as ddx of p of x dy dx plus, or rather minus actually, q of x y. Okay, let's call this equation 2. Here p of x is going to be real, and once differentiable, and q of x is going to be real and continuous. Okay, that's what we will do. And then now, so if you are looking at 1 and 2, you might think that 2 is a sort of special form of 1 with r restricted, but these are actually equivalent. Okay, so yeah, we can see that. For example, you can just divide it by p of x and then show that these two things are equivalent. Okay. All right, this is worked out in the notes for you. I'm not going to be doing this here. One of the very nice features of this Sturm-Liouville operators is that they're self-adjoint with respect to the inner product. So let us show you that. So remember what f and g were. So the inner product is given by integral. So a to b fx star g of x d of x. So that is the inner product. So the Sturm-Liouville operators are going to be self-adjoint with respect to the inner product, provided that they obey appropriate boundary conditions. So let's do this. Okay, so L of x, L of f on g. So this is what this is integral a to b of d dx of p of x df star dx minus q of x f star x, this on g of x dx. All right. So the first one is P df star dx g. This you need to evaluate at a and b minus integral of a to b p of x df star dx dg dx minus q x f star x and g of x. Okay, so I'm not going to put these x's here anymore, so this is dx. All right, so what do we get? So we also so what we get is p df star dx g minus p f star dg dx. We group these two together at a and b, plus we have integral. So we've just rearranged things so you can try to work this out. So this is f star. So ddx of p dg dx minus q g dx. Okay, so I've suppressed again dependencies on x. So what is this? So you see that this is p df dx g minus f star dg dx. This on a and b, plus now what you have is the following. This is f into L of g, right? So we have just rearranged things, and you can go through with the algebra and you'll see that this is true. So as long as your boundary term goes away, you have this being equal to this, and these are self-adjoint operators. So you need that this term has to be equal to 0. And so this is, so provided we restrict our attention to functions that obey this particular boundary condition, we have been able to show that the Sturm-Liouville operator is self-adjoint. Okay. So examples of such boundary conditions are the following. If we choose f as all our functions above, so we can have b1 f primed a plus b2 f a is equal to 0, and c1 f prime b plus c2 f b is equal to 0. These are examples of f stands for all our functions above. Okay, so these are examples of boundary conditions that stand for all of these things above. Okay, so the b1 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 b2 c1 c2 are constants which and not both equal to 0. Okay, so we must choose the same constants for all our functions. And for example, what we can do, we can take px to obey pa equal to pb, and we can say that all our functions are periodic, so that fa is equal to fb and f prime a is equal to f prime b. This ensures that the contribution at each boundary just goes off. So this is nice. So we have been able to show that Sturm-Liouville operators are actually self-adjoint. Now let's go a little further. Okay, so we're going to be interested in something called weight functions. So just as in the case of finite dimensional self-adjoint matrices, these self-adjoint operators will also have special properties. And what we want to do is we want to first define something called a weight function. Okay, so let's do this. So weight function w of x is a real valued non-negative function that has at most finitely many zeros in the domain between a and b, and an eigenfunction. So this is real valued non-negative function that has finitely many zeros in the domain AB. And now an eigenfunction of lambda, and so eigenfunction is going to be so that an eigenfunction of this particular operator, so L of yx, where yx is the eigenfunction, is going to be given as wx yx, where this wx is now the weight function. Okay. Fx. Given an eigenfunction y, we can always find a corresponding eigenfunction of weight 1 by replacing. So if you can find an eigenfunction of weight 1. Of course, what you have to do is you take y tilde, and you just have something like w of x L. And what we can do is we can replace L of y with so replace this with replace 1 over square root of w L of y tilde by root w. So the weight function does not represent anything new, but it's just a convenient thing for many purposes. So let's just treat it. Let's just choose to keep it as well. Okay. The inner product of weight, again, we're going to keep these weight functions floating around. So the inner product of f and g with weight w is going to be defined as the integral from a to b f star x g of x. Now we're going to multiply it by the weight function. And since w is real, f of g of w is going to be f of gw is equal to fw of g. Okay. So the inner product is not non-degenerate if f is continuous. So f of fw is equal to 0 would mean that f is equal to 0. And what do we want to also say? So let's so f and f of w is integral b a to b modulus of f squared omega of x dx. So this is an integral of a continuous positive function, and we have also assumed that w has a finite number of zeros in this in this interval a and b. So this integral is 0. So this integral has to be 0 only if f is equal to 0 identically. So so this is a non-degenerate. I mean this inner product is non-degenerate. Okay. All right. So the first property of this Sturm-Liouville operator, after we have done all of these things, is that the Sturm-Liouville operator is going to be Sturm-Liouville operator is going to be is going to have has real eigenvalues. Like yeah, I mean in the other case. So this is simple to see. For example, lambda of f of w is equal to f of lambda of w is equal to f of L of f is equal to LF of f, which essentially means that this is lambda star of f with f of w. So that essentially implies lambda is equal to lambda star. Okay, so that's one. And then again, the same thing. What we have seen for the matrices. So eigenvalues. So eigenfunctions with distinct eigenvalues. But same weight function are orthogonal with respect to the inner product of weight W. This is something that I'm not going to prove. This is very simple to prove. Leave it as an exercise. Now, given a self-adjoint operator L, we can form an orthogonal set of its eigenvalues. I mean, orthonormal set of its eigenvalues what we will do is that, okay, so orthonormal set y1 x to yn x, where yn x is equal to yn x by square root of integral a to b yn mod squared omega x dx, where these small yns are unnormalized. I mean, these are unnormalized eigenfunctions. Right. Finally, after making a particular choice of boundary conditions, one can also show that the eigenvalues form a countably infinite sequence with lambda 1, lambda 2, etc., and lambda n going to infinity as n goes to infinity, and that the corresponding set of eigenfunctions y1, y2, and so on. So let's sort of, just one thing that I needed to do here is that, yeah, let's just put some more dots here. Yeah, and this the set of yeah, I mean, orthonormal eigenfunctions y1, y2, and so on form a complete basis for the functions of a and b that satisfy the boundary conditions. Okay, so quickly, eigenvalues form a countably infinite sequence, lambda 1, lambda 2, dot dot, with modulus of lambda n going to infinity as n goes to infinity, corresponding orthonormal eigenfunctions y1 x, y2 x, dot dot dot, form a complete basis for functions on AB. Okay, satisfying these particular boundary conditions. So any function that you can write down so any function in this particular domain which obeys these boundary conditions can be written again as we did for the things earlier, can be written as fn yn of x, where fn now is given as a to b yn star x f x, also have the weight function wx dx, which is just yn of f with the weight w. Okay, now you can envision where we are going with this. So the important point is that fx can be expanded as a discrete sum, like just like for the Fourier series. This is indeed remarkable, as these YNs that we have tried to define here involve no hint of discreteness at all. What happens is that this discreteness arises because this domain AB is compact, and this is because and because of these sort of boundary conditions that we put on it. Okay. Now, since we stressed that this is happening, this is something similar to the Fourier series, let's just see a few explicit examples which will make this a little clearer. Okay, so some examples here. So let's take the simplest non-trivial case, and let's start off with AB being equal to minus L to L, and we impose homogeneous boundary conditions such that all functions are periodic. That is, so all functions are periodic. That is, f of minus L is equal to f of L, f primed of minus L equal to f primed of L. So if we also choose px equal to 1 and qx equal to 0, then the operator that we have in hand just reduces to d2x dx squared. It can be easily shown that this is self-adjoint when acting on the functions that obey these boundary conditions. Okay. Now, furthermore, let's choose omega x equal to 1. And we do this identically. Okay. Now, our eigenfunction equation is L of y of x is equal to minus lambda y of x. If lambda is less than 0, then the only solution that obeys the boundary condition is y of x is equal to 0. If lambda is greater than 0, then there is a basis of solutions this is given by y of n. X is exponential of I n pi x over L, for lambda is n pi by L squared, where n is an integer. Now, this is simply just the Fourier series. Okay, so that was example 1. Now let's look at another example. Let's call this example 2. And now we have this equation h half h double primed minus x h primed is equal to minus lambda h of x for x belonging to R. So this is subject to the boundary conditions. Boundary conditions of h of x is polynomial as x goes to infinity, and in particular This means e to the power minus x squared over 2 h of x goes to 0 as mod x goes to infinity. Okay. First thing to notice that this guy is not in the Sturm-Liouville form yet. So first we find out the integrating factor. So e of x is minus integral 0 to x 2t dt. This is just minus x squared. So, then we can rewrite this above as the following. So this is d dx of e to the minus x squared dh dx. This is minus twice lambda e to the power minus x squared h of x. All right, so this particular equation is the Hermite equation, as you guys would surely be familiar with. This is important for combinatorics, probability, and the thing I guess you guys are most familiar with is the simple harmonic oscillator in quantum mechanics. Very good. Now, the condition that we stated that hx grows at most polynomially at large x is now understood by the following, right? So what we have is, if we have the integral of minus infinity to infinity f star d dx of e to the minus x squared dh dg dx of dx, this is simply minus infinity to infinity df star dx e to the minus x squared dg dx. This has to remain finite, right? This has to remain finite. So this for this to remain finite, we have the boundary conditions. If f and g are sort of regular along R, this is going to be true so long as the integral is suppressed at large x's, and that is what this. I mean, so the fact that this decays at large x just ensures this. All right. So yeah, so that was that. Okay, so the non-trivial solutions that are regular for x's if the eigenvalues. So non-trivial solutions regular for all x belonging to R. This happens if and only if lambda is a non-negative integer, and then h of n of x is given by minus 1 to the n e to the x squared dn dxn of e to the minus x squared. Okay, so these HNs are what are called Hermite polynomials. Okay. So that was, so these are orthogonal with respect to the weight function. W of x is equal to e to the minus x squared. So this is hm of hn e to the minus x squared is minus infinity to infinity hm of x hn of x e to the minus x squared dx. This turns out to be, you can figure this out, 2 to the n square root of n into n factorial. Okay, so that was that. So what we have learned is we have learned how to deal with these, and we have learned how what we did from the start of this lecture is we have started out with self-adjoint matrices and shown you how we can solve, for example, a linear equation in terms of these eigenvalues and eigenvectors. And then we made an analogy with differential operators, and the same way as we solved uh, the linear equation there, we are going to be solving a differential equation here. What we do is p yeah, so these things, if a, p, and a are what are supplied to you, and f of x is also supplied to you, you need to find what y is, right? So y is, if you wish, the in the formal solution would be yx is L inverse into f of x, right? So that's what the formal solution would look like. We have written L in a form like this, so that we can now show that this is actually self-adjoint when when we are looking at a particular boundary condition. So when our solutions have a particular set of boundary conditions that look like this, then we would be able to employ the methods very similar to what we had earlier. So then I showed you that here similar things like the Sturm-Liouville operator has real eigenvalues, and then it has eigenvalues with distinct eigenfunctions with distinct eigenvalues are orthogonal to each other, and we showed this. And so what happens is, and we also have that, we have this, what we can do is we can write down any function. So these normalized orthonormal eigen functions y1 and y2 forms a basis in the for the functions, and functions can be expanded in a discrete series like this. So again, whatever we did from the point of view of the matrices and the linear equations, very similar things just go through here. And then we showed you a few examples, which then we showed you the Fourier series, and we also showed you what happens when you're looking at the Hermite equations, and these eigen functions actually become these Hermite polynomials. Okay. So this was a quick run through of the Sturm-Liouville methods of trying to deal with ODEs. This is going to be of some importance going forward, because we are going to be trying to understand Green's functions from here. and it would be of importance to try and see this. Okay, so that's it for the day. This lecture was a bit long, but I hope this has been useful.